Welcome to this deep dive, where we unpack the latest and greatest in AI research. Today, we're digging into a really interesting paper, DDT, Decoupled Diffusion Transformer.
Yeah, this one's from researchers at Nanjing University and ByteDance Seed Vision.
And the results are pretty staggering. We're talking FID scores on ImageNet like 1.31 at 256 by 2556.
And 1.28 at 512 by 512. Truly state-of-the-art stuff.
But maybe the real kicker, especially if you actually train these things, is the speed. They're saying it converges 4 times faster than older diffusion transformers.
4 times. That's huge. Think about the compute savings, the iteration time.
Exactly. And the code is out on GitHub, which is great. So our mission today is to figure out how they did it. What's the magic behind DDT?
Right. It's all about tackling this core problem in how these models usually work.
Okay, so let's get right into that. What's the fundamental issue DDT is trying to solve?
Well, the paper calls it an inherent optimization dilemma in standard diffusion transformers.
Okay, dilemma. What's conflicting?
Think about the denoising process. You start with noise, right? And step by step, you refine it into an image. In traditional models, the same parts of the network, the same modules, had to do 2 jobs at once in each step.
Which are?
They need to understand the big picture, the low-frequency semantics like, is this a cat or a dog? And also reconstruct the tiny, high-frequency details, the fur texture, the sharp edges.
Okay. I can see how that might be tricky, like trying to paint a detailed portrait and sketch the overall composition with the same brush simultaneously.
That's a great way to put it, yeah. When it's focusing on the broad strokes, the fine details might get blurred or lost, especially early on when there's lots of noise.
And vice versa. If it focuses too much on pixels early on,
then it might struggle to grasp the overall meaning, the semantics. The paper also mentions that just supervising on raw pixels isn't great for learning robust semantic understanding anyway.
So this juggling act makes things inefficient and maybe limits the quality. How does DDT get around this? What's the core innovation?
Decoupling. That's the key. They split the work.
Okay, split how?
They created 2 specialized components. First, there's a condition encoder. Its only job is to look at the noisy input and figure out the semantics. What is this image supposed to be?
Got it. So one part focuses purely on the what. What's the second part?
The second is the velocity decoder. This one is laser focused on generating the high frequency details. It takes the semantic understanding from the encoder and the noisy image, and it predicts the velocity, basically, how to adjust the pixels to make the image cleaner and more detailed.
Encoder for meaning, decoder for details. The paper's figure 1 probably shows this side by side, right? The old way versus the DDT way.
Exactly. It contrasts the standard approach with this new decoupled design very clearly.
And this separation is what leads to the faster training and better results.
That's the idea. By letting each part specialize, you remove that optimization conflict. The encoder gets really good at semantics without worrying about pixels, and the decoder gets the semantic guidance it needs to nail the details.
Plus, you mentioned it helps with inference speed, too.
Yeah, that's a really neat side effect we can talk more about later. It involves reusing some of the encoder's work.
Okay, cool. So we get the core concept. Let's backtrack a bit to those limitations of the older models. Why exactly were they so slow to converge?
Well, it largely comes back to that conflict, that juggling act. Trying to optimize for both low-frequency semantics and high-frequency details within the same modules at every single step just isn't very efficient. The learning process gets slowed down.
And that point about being limited in extracting semantic representation due to raw pixel supervision, what does that really mean for the model?
It means the model might learn to just match pixels and textures without really understanding the concepts in the image. It learns correlations, sure, but maybe not the deeper structure. Think of it like
memorizing phrases without knowing the grammar.
Exactly. You can reproduce things, but you don't have a deep grasp. It takes a lot more training data and time to get good results that way.
Okay. The paper points to figure 3, showing the process for SciT XL2. What should we notice there?
Figure 3 shows the denoising journey from noise to image. What's striking is how much time, especially later on, say, from time step MAMPATE 4 to 1.0, is spent just generating the fine, high-frequency details. A lot of effort goes into that final polish.
And if the initial semantic sketch wasn't great,
then that polishing stage has to work much harder, trying to figure out the details while staying true to an unclear plan. It's inefficient.
They also bring up Lemma 1. Without getting lost in the math, what's the gist?
Lemma 1 basically says something about how frequency information changes during denoising. As time goes on and the image gets less noisy, it increases. Encoding the overall structure gets easier because it's less obscured.
Makes sense.
But decoding the remaining high-frequency details accurately actually becomes more complex.
So early on, semantics are hard because of noise. Later on, details are hard because you need precision. That trade-off again.
Precisely. And it fuels that optimization dilemma. To prove this, they did an interesting experiment shown in Figure 4. They played around with how much computation they gave to different time stages inside TXL2.
And what did they find? I remember you saying it was a bit counterintuitive.
Yeah. They found that giving more compute to the earlier, noisier time steps actually improved the final image quality, the FID score.
Really? More power to the noisy part helps.
It strongly suggests the real bottleneck is getting that initial low-frequency semantic understanding right. If you invest more compute there, you build a stronger foundation, and the rest of the process becomes smoother and more effective.
That makes perfect sense. Build a good blueprint first. Okay, so knowing the problem, let's break down the DDT architecture itself. How does this decoupled design work in practice?
So you have the two main pieces, the conditioning encoder for semantics and the velocity decoder for details. And it's all trained using linear flow diffusion.
Let's focus on the condition encoder first. What's it built from? What goes in?
Architecturally, it looks a bit like DIT or SIST, those transformer-based models. It uses stacked blocks of attention and feed-forward networks. They mention some micro-design improvements, though, and specifically don't use the long residual connections found in some transformers.
Okay, and the inputs?
It takes the noisy image, $6, the time step $, and optionally a class label $.
And it outputs this self-condition feature. What is that, conceptually?
Think of ZIST as a compressed representation of the meaning of the noisy image at that specific time. It's the encoder's understanding. Equation 2 in the paper defines it. The time step and class label info get injected using something called ADL N0.
ADL N0, adaptive layer norm. What's its role?
Yeah, it's a way to effectively feed the time and class information into each block of the encoder so the model knows when in the process it is and what it's trying to generate.
Now, this representational alignment using Dino V2 sounds important for getting good semantics. How does that work?
It's crucial. They want the encoder's understanding, DIT and DILs, to be consistent as you move from one time step to the next. So they borrow an idea from the RPA paper. They take an intermediate feature map from the encoder, project it using a small MLP, and then force it to be similar using cosine distance, as shown in equation 3, to the representation of the same image patch from a powerful pre-trained vision model, Dino V2.
So it's like saying your internal understanding should match how this really smart pre-trained model sees it, a kind of external guidance.
Exactly. It guides the encoder to learn smooth, meaningful representations. This directly helps the T be consistent across time steps, and the paper says it really speeds up convergence. Plus, it indirectly helps the decoder too.
Okay, encoder makes sense. Now the velocity decoder, similar structure.
Yep, also stacked attention and FFM blocks. But its inputs are different. It gets the noisy image, the time step, the irisers, and critically, that semantic feature C-tail is from the encoder. That's in equation 4.
Notice the class label isn't fed directly here.
Right. The assumption is that the class information is already baked into detail by the encoder.
And the decoder's job is to predict velocity. What is velocity in this context?
In this flow matching framework, $5 is essentially the direction the noisy pixels away need to move in to get closer to the clean image distribution. It's the update direction the decoder learns to predict.
And they also inject ZOLs into the decoder using ADL N0 again. Why repeat that?
It's to reinforce the semantic guidance throughout the decoder's processing steps. It ensures that detailed refinement stays consistently aligned with the encoder's semantic plan. The whole thing is trained with a standard flow matching loss, equation 5.
Right, minimizing the difference between predicted velocity and the true velocity needed.
Okay.
Encoder for meaning, decoder for details, linked by ZAL dollars. Now this inference acceleration via encoder sharing, this sounds clever.
It really is. Because they trained the encoder using that representation alignment, the resulting semantic feature SINDOLR is pretty stable between nearby time steps. It doesn't change drastically from step to step plus along.
Figure 5 shows this similarity.
Yeah, figure 5 plots the cosine similarity, and it's quite high, even between adjacent steps. Even silly near pure noise is pretty similar to the next steps of Ziller.
So, if SEAL isn't changing much, why recalculate it every single step during sampling? That sounds wasteful, especially if the encoder is heavy.
Exactly. You can just reuse it for a few steps. That's the core idea.
How do they formalize that?
Equation 6 lays it out. If you have dollars total sampling steps, But you only want to run the expensive encoder times, where you define a set face of dollar time steps, where you do run the encoder.
And for the steps not in FIS?
You just reuse the ZL calculated at the previous time step in dollars, so you get a sharing ratio of $1 and $1.
Simple enough. But how do you choose which dollar steps to recalculate on? They mention uniform encoder sharing.
That's the basic way. Just run the encoder every num steps. So if NDO to $5 and T5 usage, you run it every 5 steps. They know Deep Cache did something similar for UNets.
But DDT might be better suited for this.
They argue yes, because their encoder's output, ZLR, is explicitly trained to be more consistent due to the representation alignment.
Okay, but uniform isn't always optimal. They propose statistic dynamic programming. Sounds fancier.
It is. It's about being smarter about when to recalculate. The idea is to use the actual similarity between different time steps.
How?
First, you pre-compute a similarity matrix solver showing how similar ZLs is between any 2 time steps, say E8 and $.
Okay.
Then, you frame the problem. Find the recalculation points that minimize the total cost of reusing stalls in between those points. The cost is basically higher if the reuse is very dissimilar to the ZL you skipped calculating.
Right, you want to recalculate just before the representation is about to change significantly. How does dynamic programming solve this?
It's a classic shortest path problem. They define Quashi as the minimum cost to reach step toss using Taylor calculations, and Polkey tracks the path. Equations 7 and 8 show how they calculate the cost, considering reusing cell for steps between $. and $.
So it looks back at all possible previous recalculation points, DJ and XDOL, and finds the cheapest way to get to step dollars using Torel calculation.
Exactly. Once you compute the whole cost and path matrices, you backtrack from the end state, you should find the optimal set dollars time steps.
That's much smarter than just uniform spacing. It adapts to the model's actual behavior. Okay, let's get to the results. How did DDT actually perform?
They tested mainly on ImageNet 256 by 256 and 512 by 512, standard setup. Atom Optimizer A100 GPUs, 250-step Euler sampler for evaluation.
And importantly, they made sure their baseline comparisons were fair by improving them first.
Right. They incorporated recent tricks like SWIGELU, ROPI, RMS norm into baseline models. They even reproduced the RPA results and slightly beat them, which adds confidence.
Good practice. So how did DDT compare against these strong baselines after 400K training steps?
Table 2 shows it pretty clearly. DDT models consistently beat the improved baselines. DDT V2 was 2.8 FID points better than improved RPA2.
Wow, 2.8 points is a lot at this level.
It is. And DDT XL2 beat RPA XL2 by 1.3 FID points. They also noted that the RPA model seemed to be hitting a performance ceiling, while DDT kept improving.
Significant quality jump. What about that training speed claim, the 4x faster convergence?
Table 1 back setup. DDT reached convergence, hitting really good FID scores, in roughly a quarter of the epochs needed by REPA and others.
So just 80 epochs got them great results.
Yeah, with classifier-free guidance, DDT-L2 hit 1.64 FID and DDT-XL2 hit 1.52 FID in only 80 epochs. Pushing training longer, DDT-XL2 got that 1.31 FID at 256 epochs, and even 1.26 FID at 400 epochs on 256 by 256, really close to the VAE's limit.
That speedup is massive for practical use. Did it hold up at 5.2 by 512 resolution?
Yep. They fine-tuned the 256 trained XL model on 512 by 512 and got a state-of-the-art 1.90 FID, beating RVP by 0.28 FID. Okay, revisiting the encoder sharing for inference, what were the actual speedup numbers and quality trade-offs?
Figure 6 and Table 4 show this. They got really significant speedups with very little quality loss. Like a 2.6x inference speedup only increased the FID from 1.31 to 1.36. That's almost negligible.
2.6x faster for basically the same quality, that's huge. And the dynamic programming approach was better than uniform sharing. Yes. The statistic dynamic programming method consistently gave a smaller FID increase for the same speedup compared to just uniform sharing. It makes better choices about when to recalculate.
Fantastic. Lastly, the ablation studies. Anything jump out about architectural choices?
The encoder-decoder ratio was interesting. Figures 7 and 8 show their results. Generally, as the models got bigger, having a relatively larger encoder seemed better.
How much larger?
For their base model, 8 encoder layers and 4 decoder layers was good. But for the large model, they found, somewhat surprisingly, that a very aggressive 20 encoder layers to only 4 decoder layers worked best.
Wow, really heavy on the encoder.
Yeah, and that finding influenced their XL model, which used 22 encoder and 6 decoder layers.
I see.
It suggests the semantic encoding part becomes increasingly critical at scale.
Interesting. What about the decoder block types? Did it matter much what they used there?
Table 5 shows this. Their default attention plus MLP blocks worked best. But interestingly, even using simple convolutional blocks in the decoder gave pretty decent results.
Really? Even with basic convol blocks?
Yeah. They think this shows how effective the decoupling is. If the encoder provides a strong enough semantic signal, even a less complex decoder can still manage to generate good, high-frequency details.
Okay, this has been a fantastic breakdown. Let's try to wrap up the key takeaways.
Sure. The absolute core idea is the decoupled architecture. Splitting the semantic encoding and detailed decoding into separate modules, that's the main innovation.
And this simple-sounding idea solves that core optimization problem and unlocks some major benefits.
Definitely. We're seeing new state-of-the-art image quality on ImageNet, which is a tough benchmark.
Plus that incredible 4x faster training convergence.
Right, huge for practical development.
Sure.
And then there's the Inference Speedup from encoder sharing, which works so well because of the decoupled design and representation alignment.
So looking bigger picture, what does DDT mean for the field?
Well, it directly addresses a major pain point of diffusion models, the long training times. This could make high-performance models more accessible and speed up research.
And the decoupling strategy itself might be applicable elsewhere.
I think so. It suggests that breaking down complex generative tasks into specialized subproblems could be a really fruitful direction for future work, not just in images, but maybe video, 3D, other areas.
That's a great provocative thought to leave folks with. If decoupling works so well here for encoding what versus decoding how in images, where else could we apply that principle? What other complex generative processes could be untangled into specialized parts? Maybe video motion versus appearance, or 3D structure versus texture.
Lots to think about there. For anyone listening who wants the full technical details, definitely check out the paper on Argue and the code on GitHub. It's a really solid piece of engineering.
Absolutely. A big step forward for diffusion models. Thanks for walking us through it.
My pleasure. It was a fascinating paper to dive into.